aware of the ventilation from the fumes of the welding flux and welding gases. Also, if you're welding in confined space, provide ventilation and have some body to make sure that you are okay, and keep all the electrical connections safe. All the cables should be clear of in the not in the right of way of people, so people don't get stuck on the cable. And when you are welding with explosive gas or explosive anything that it can be explosive, please take care of the distance, and also just beware of the environment during welding. So after the safety moments, I will try to scope my presentation. I hope everything can be completed in the time allocated to me. So this presentation mainly related to the arc welding, and the materials are carbon steel, stainless steel, and nickel alloys. And I will only just speak about corrosion and some metallurgical defects during the welding. Frankly speaking, I'm not a welding expert, so I will not discuss about welding process. I will not discuss about any mechanical defects that may arise from the welding. Also, other metals, for example, like aluminum, copper, and non-metallic materials like plastics or FRP, I will not discuss in this presentation. So the scope will be just arc welding, carbon steel, stainless steel, and nickel alloys, corrosion problems in the welding. And this presentation is very basic. So if you are already an expert in welding, you might be bored by this, but this is what I want to. I want some like if there's a junior engineer, so they can take something from this presentation. First is for people to know what is the common welding parameters that can influence corrosion in the materials. Also, what are the possible corrosion problems in the weldments of various materials, and to know importance of corrosion qualification tests before welding. And last one is to know additional information that I hope can reduce probability of weldment corrosion. And for this whole presentation, there will be a lot of abbreviations. I'm trying to shorten a lot of things just to make it more clean to the eyes. So this is, if you find CS, it means carbon steel, SS means stainless steel, HAS means heat affected zones, corrosion resistant alloys. It's a combination between stainless steel and nickel alloys. SCC, stress corrosion cracking, and PWHT is a post-weld heat treatment. And starting with corrosion, what is corrosion? This is my own words, so this is what I think about corrosion. So it is reaction with environments causing the degradation of the materials and rendering it usable over a certain period of time. So it might be fast, it might be take some time, but it will degrade. And the problem is it cannot be seen after you weld the materials. It's not easily seen. You might see it after a few days or few months or few years, but it cannot be seen immediately. So, and then corrosion is something that influences significantly from the pressure, temperature, and the concentration of the corrosive substances. Normally, the main mitigation, in general, there are 5 mitigation of corrosion. First is using proper material selection. Second is cathodic protection. Third is you coat the materials to avoid contact with the corrosive environment. Fourth is chemical treatment. You change the environment. And The fifth is corrosion monitoring. You just monitor the corrosion. It's already happened, but you can monitor uh, to avoid failure. So before failure, you already know that this is going to failure, and you can mitigate. You can change the materials, or you can repair the materials. And the aim for the welding is to get not better corrosion resistance, but at least similar with the parent material. And this is what I think why the weldments area is more susceptible than the parent material. So in the parent material, for example, let's say a pipe or a plate, it's produced in a factory environment. It's a mass production. So the process of production is mechanized, automatic, and they make well they make the material almost every day. They produce a pipe 1,000 tons probably every day. So it's a it's a uniform process. The microstructure of the material can be easily controlled by heat treatment because the size are limited, so it's easily put in the furnace and then heat treated to get properties according to what the customer wants. Chemical composition are uniform. It is already standardized. For example, in STM, and there is no heat affected zones. And it's totally different from the welds. It's produced mostly at field. It's the worst. Probably still you can get better result in the workshop. The process parameters are varies and a lot of manual works. Microstructure are not uniform. It's like a chill casting in combination with segregation of the chemical elements. And normally filler metals are having different composition from the parent material. So you can get a very different chemical composition between the weldings and the parent material. And the last one is in the welding, you have heat affected zones. It is, I'll explain later about the heat affected zones. And what make weld are susceptible to corrosion is the segregation of the chemical elements. It's the probability of secondary phase precipitation. It's a possible of heat affected zone. The grains have recrystallization, also probably grows, and also vaporized alloying elements. When the parent metals get heated, some of the part of the chemical elements get vaporized because of temperature that reach thousands of Celsius. Possible contamination of the weld pool from oil, grease, from oxygen. And when you weld, you put a very high temperature, and it can give you residual stress after the weld is cool. Also, rapid cooling may happen during welding, especially during in arc strikes or the area of unmixed zones. And surface finish. So after weld, you need to clean the surface again to avoid reduction of corrosion resistance. So you can find heat tint on after the weld. You can have slacks, and you can pickle the surface to get better corrosion resistance. Also, the weld can impose galvanic action. For example, if the chemical composition are very different from the parent material. Previous slide is from the welding, but this slide is from the environment that can cause the corrosion. So if the fluid have oxygen, definitely you can get corrosion. If the fluid is highly conductive, also it make it easier to get corrosion. High flow, high temperature, high pressure, presence of impurities, the total fluid chemistry, all this is all variables that can affect the corrosion risk. And this is the Weldment zones. This is a very broad explanation. So if someone that have a limited knowledge in welding, you can learn more by googling and or reading any handbook. So this is just a general explanation. There will be a fusion zones in the weldment. So this is a melted area from filler metal, including some current metal also dilute in these fusion zones. And the main concern is unmixed zones. There is a fusion, is a melting also, but the parent metal is not dilute with the filler metal. So it's melting and then cooled rapidly without any mixing from the filler. It's like autogeneous welding. And the second zones are heat affected zones. It is area of the parent metal that is not melted, but it experiences high temperature. So the microstructure is changes permanently. This is an example for the welding zones. So as you can see, the microstructure of the weldments are dendritic. This is from the like a chill casting, and the closest one is the unmixed zones, and then you can find grain growth, recrystallization, depends on the temperature. This is example in a carbon steel material, and if you see in the microscope, this is what you can see. This is the Weldment area where you can have this dendritic microstructure, and then you have this grain growth. You have this recrystallized grain in the heat affected zone, and this is the base metal where it's the same properties as the original material. And this is what the unmixed zone that I said before. Why this is a concern? Because this is the area. It's not always happen, but if this happen, this the area that will have a very low corrosion resistance, because it doesn't have the mixing from the filler metal, and this is rapidly cooled. So when you see this is, you can see that this is black. It means that this is preferentially attacked by the chemical. This is the welding. This is the weldments, the fusion zone. This is the base metal. So you can see that this is rapidly attacked, but the others are still okay. And what are the common corrosion that happens on the weldment area? I have compiled some of the corrosion that I know. This may not everything, but this is what I know mostly, and this is what I normally mitigate during when I write the specification for corrosion prevention. So there will be preferential wet corrosion, sensitization, knife line attack, secondary phase precipitation, liquid metal embrittlement. This is all I can consider metal loss corrosion, that the metal will be losing metals over time. So this is predictable and it can be monitored. The second one is SCC, or stress corrosion cracking. This is the worst of all, because normally it cannot be predicted when will it happen, because it's a crack. When the crack happen, then it's very easy to lose the pressure containing strength when you find cracks. And these cracks can be caused by many factors. It can be from chloride, polyionic acid, sulfide, caustic, amine, and carbonate. All of this chemistry normally we can find in the oil and gas, chemical, and petrochemical. So there might be other corrosive environment that I didn't mention in here because it's not my specialty. I don't have the knowledge for that. If, for example, if you're working in pulp and paper, you might have another another cost from the for the corrosion. But I'm not mentioning it because I don't have that knowledge. So I will discuss one by one of these Weldment corrosion types. So first is the PWC, preferential wet corrosion. Affected materials are carbon steel. The corrodant is the corrosive elements that can cause the corrosion. Acidic water or low pH water, seawater, high CO2. So it's like a carbonic acid. This preferential wet corrosion is the weldments are corroded faster than the parent material. And to mitigate is to use matching consumables and correct dosage of inhibitor. The reason why, because the weldments have different chemical composition and microstructure than the parent metal. So when consumables used are not similar, not close to the parent material, it can be preferentially attacked. It might have a lower corrosion resistance than the parent material, so it get attacked even more because of the galvanic action. And why is the mitigation of correct dosage of inhibitor? Because this is also happen when you have a system when corrosion inhibitor is used. Normally, when we use the corrosion inhibitor, we qualify how much inhibitor we need to add to the system to make it corrosion, to make it long lasting, make it the corrosion rate getting low. But this qualification normally we do with the parent material or corrosion monitoring like a coupon or corrosion probe, and we didn't do it from the weldments. And the problem is that the weldments is not fully protected by the corrosion inhibitor, so it can get preferential wet corrosion, preferential wet corrosion as well. So when you use corrosion inhibitor, normally the best practice is to increase the dosage a little bit to make sure that the weldments are protected. And this is the problem when we are forced to use matching we are forced to use consumables that is not matching. For example, if we are adding nickel to increase the low temperature resistance, to increase the impact strength, it can increase or it can decrease the corrosion resistance. So it's hard to predict if the PWC will happen or not. So the best option is to use matching consumables always to mitigate this problem. So you don't have any chances to about this PWC. And this PWC happen mostly in very corrosive environment. If it's mildly corrosive or is normally doesn't happen. So you get the same corrosion resistance between the parent material and the weldments. But if it's in the very corrosive environment, then you can have it different. The weldments probably get attacked faster than the parent material. So this is just an example in weldments PWC in a CO2 containing a brine. So you have chlorides there, you have CO2 there, and you get if you can see that the parent material are very less attacked, but the weldment is attacked very fast. This is called galvanic action. So this is anodic, this is the cathodic. So the small anodic have to protect all the cathodic sides. So this is have a accelerated corrosion. And this is the testing that was done by TWI. So they're testing if using consumables with different chemical composition, what is the effect? So you can see the weld are the black one, and the rest are, this is the white, this is the parent, the beside this is the heat affected zones. So as you can see, the result is inconsistent. Sometimes in the similar, even in the matching consumables, you can have higher corrosion in the welds, and sometimes you don't. And in the nickel addition welds, 1% nickel, you get high, very high weldment corrosion. It is silicon, you also have a very high corrosion. But this is the environment in low chloride solution, 60 degrees and 1 bar CO2. But if you change the environment, then it's going different. This is high chloride CO2 and this is same temperature and same CO2, but chloride is high, you get similar corrosion rates. So as I said, it is unpredictable. So the best thing is just to use matching consumables. So okay, previously it was PW corrosion for carbon steel. Now it's a sensitization problem. This is for stainless steel and nickel-based alloys. So when the stainless steel or nickel-based alloy are sensitized, and any corrosion can start on the material. So any corrosion, see water or acid or anything, because it's already losing its corrosion resistance. So this sensitization is the reaction between carbon and chromium in the stainless steel or nickel-based alloys. So one of the mitigation method is to use lower carbon, or to add stabilization chemical elements, either niobium or titanium. This takes carbon easier than the chromium. So when you add this is more this reacted first with the carbon, so the chromium can stand by itself. It doesn't react with the carbon. Or if there is no, if you don't have any choice, then you have to modify welding process to get a faster cooling rate, so that the reactions, there is not enough reactions for the chromium and the carbon to react. So this is the mechanism. The precipitation of chromium with the carbon, so it creates chromium carbides in the heat affected zones grain boundaries, and it's happen on the temperature between 500 to 900 in general. It's normally affect during the cooling of the welding process. And what is the chemical composition? Is chromium 22 and C6. So it means a 6 carbon atoms, it takes a lot of chromium atoms. It's 1 carbon to 4. So even small amount of carbon in the materials can take a lot of chromium from the metal. So when the grain boundaries doesn't have enough chromium, then you can have corrosion in that area. And for this is just information. Even if you use low carbon steel and addition of the chemical elements, it doesn't make it immune, but it's prolong the precipitation time. So if you have this equipment working at the 500 or 600 Celsius for years, then I know 10 or more than 5 to 10 years, then you may have this problem. So let's see the background structure. And this is for 304 without L, so this is not low carbon. You can see the black lines on the grain boundaries. So this is the chromium carbides. and the corrosion will start on the black area. This is the when you have a macro structure. In the left is the micro. This is the macro. So you can see it's the happen in the harsh area. The weldment itself, the fusion zone is unaffected. It has very good corrosion resistance, but it affects the heat affected zones. It get preferential. It get corrosion because of the lack of chromium. And this is the curve, the cooling curve of the stainless steel with variation of carbon content. So if you use low carbon stainless steel, normally the specifications say maximum is 0.03 carbon. It's in here. So when the welding are cooling down from high temperature, for example, let's say this one 900, if it's cooling down very fast, you will not have sensitization because you didn't the lines didn't contact with any of this, with any of the nose. We call this nose. So even if you have, let's say, 0.06 to carbon, it's still safe because you have this very fast cooling. But if you have slower cooling, or let's say a multi-pass welding, so it stays in this region of temperature for some time, the cooling temperature will reach one of these nodes, and then chromium carbide start to precipitate. So low carbon stainless steel is set at 0.03, so the cooling have enough time. It's like 1 hour time to cool before it start to sensitize. Even lower carbon, you can have longer time to sensitize. So this is 0.03 is the L grade, for example, 304L or 316L is this line. So I would say it's pretty safe for any welding to cooling not to reach this line. And it's not only stainless steel, also nickel alloys. Although it's very rare to happen, nickel based alloy also can have this sensitization. It's the same, not the same curve, but the same concept. So when you cool the metal and it contact the nose, then you will have this sensitization. So try to avoid cooling time, long cooling time, so that it will not contact with the nose. This is just example. So what is the difference of the stainless steel? For example, 304, you have maximum carbon 0.07, but if you use L grades, you have maximum 0.3. And this is the stainless steel with stabilization elements. 321, you have titanium. 347, you have niobium. You can have higher carbon, 0.08, but the carbon is taken by the titanium or by the niobium. So you have no problem with the chromium carbides. It's already reacted. All the carbons is already reacted with titanium or the niobium. So there is not enough carbon to react with the chromium. And the third one is secondary phase precipitation. This is also mostly caused by weldments, affected materials, SSN, stainless steel, and nickel alloys. The same. This is all corrosive products can happen when you have this secondary phase. The mitigation is to minimize ferritic phase at high temperature. This is ferritic phase is very susceptible. It's very easy to to generate secondary phase. The concept is similar. The secondary phase is we normally call intermetallic phase. So it's the metals diffuse each other and then becomes intermetallic. And the problem is that the one that diffuse and reacted with each other is the one that gives corrosion resistance. For example, the chromium and molybdenum. And when they are reacted to each other, they cannot protect the materials. So the area surrounding this secondary phase will have very fast corrosion. And there are many forms of the secondary phase. This is this is just a generalization. So it can be from 475 embrittlement. It can be called sigma phase. It can be in the form of nitrides. And the causes are the accumulation of heating time and then reaching nose in the transformation curve. It's almost similar with the sensitization. And with this secondary phase, not only high temperature but also rapid cooling can cause this, especially with the stainless steel or alloys that have nitrides. When it gets cooled very quick, then the nitrides is reacting with the chromium normally, and then it can get chromium nitrates. So the cooling rate must be balanced, not too fast and not too slow. This is example. So this is the same, is noise like a nose, similar with the sensitization by chromium carbide before. So this for duplex, for example, duplex material have a very high ferrite content, like 40 to 60% ferrite content. So you have to cool it before reaching the nose. When you reach the nose, then you can get the secondary phase precipitation. The more high alloy, the more easier it is to get secondary phase precipitation. This is super duplex, very high alloy, so it's very fast. And this is lean duplex, lower alloy duplex. So you can have some time to have the secondary phase precipitation. And this is what happened when fast cooling of duplex. This is the weldments, the fission, and this is the current metals. And you can see in the heat opacity zones, this is cooling very fast because this laser welded is the cooling is very fast compared to arc welding. You can see the chromium nitrate precipitation, and this will be the starting point of corrosion. Liquid metal embrittlement, this is considered, I consider this as corrosion, but actually this is probably, you can consider this as the impurities, not corrosion. This is affected are stainless steel and nickel based alloys as well. So the corrodants are low melting point metals. This is not from the fluid, not from the surface, but normally it's from the contamination. So the mitigation is to clean the materials thoroughly, especially the joint. So you have a very clean joint preparation. The most often happen in the field welding. So sometimes the stainless steel is in contact with galvanized material or in contact with carbon steel, the painted carbon steel. Normally painted carbon steel have zinc content in the paint. So when it's have contact and have a residue on the joint, then when you weld the stainless steel materials, the zinc are melted as well, and the melted zincs are attacking the grain boundaries. So this is almost always intergranular cracking. So the cracking are almost in the grains. The liquid metal go inside the grains, and when cooled, it creates very high stress on the grains, and then it cracks. So this damage mechanism is not by the fluid, not by the surface, but by the contaminants. Heat tinting. This is also cause corrosion quite a lot to stainless steel. This is often we can often see this in the field. So the affected materials are oxide forming alloys. So any materials that form oxide layers can have this heat tint problem. Stainless steel, nickel alloys, titanium alloys. So when you have this heat tint, then all the corrosive product can corrode the material. So what is this heat tint? It's a layer because of the oxygen contamination. So when you have oxygen and high temperature during welding, it reacts with the metal in the material and create scales. It is not an oxide layer. It's not protective. It's scale. It's brittle and it's porous. So, and it takes a lot of chromium. So when you have this heat tint on the stainless steel surface, the below heat tint area is an area where you have a very low chromium content, and it's very easy to corrode the area at the heat tint. So normally, if it's a very corrosive condition during the weld, we ask for the welding design to have the trailing gas to make sure that there is low probability of oxygen contamination. And the problem also, why this happen a lot, because it's a color-based decision if this is acceptable or not. So it's very subjective from the inspector point of view. The inspector can accept or can reject the heat tint. So luckily they asking for repair, at least for the heat tint, so it doesn't cause any problem. Or during the weld, they ask for using oxygen measurement tools to ensure that there is no contamination. And as the equipment user, we prefer that heat tint not exist, but if they exist, there is some acceptable heat tint color that we can accept. And normally the standard refer to AWS or NORSOC. So this is example what can be accepted, what cannot be accepted. This is from NORSOC. So if you can see, this is very depend on the inspector eyes. Is he or she trained or not, or the lighting condition are good or not. So the best is the A here. You don't have the heat tint, but B is acceptable. But it's yes, I would say it's questionable. Can we accept it or not? But if the environment is very corrosive, normally even B we don't accept it. And there are the others heat tint that need to be repaired or rejected. You can see I remind all of you once more, if you need to find the references, I put it on the bottom left of the pictures. All the picture have these references, and this is for AWS. You can see what is what is the effect of the oxygen to the heat tint. The more oxygen contamination, the more dark color you have. So this is also subjective. So which number that is accepted? Is 3 accepted? Is 4 accepted? That depends on the inspectors. Number 1 and 2 is the one that we really want. This is even more pronounced when you have application in food or pharmaceutical industry. They almost always want one, no heat tint. And this is what happened to corrosion resistant when you have oxygen contamination. This is example of the duplex and high alloy austenitic stainless steel. This is 2205 duplex. This is 904L. So when the parent material, you have a very high, this is critical pitting temperature. Critical pitting temperature is the temperature when pitting happens. So the higher the temperature is, the better the material. So this is the parent material. They have a very high temperature before the metals experience pitting. And this is the welding gas argon with 5 ppm oxygen. So there is reduction, but not a lot. But if you see here, if it's reached the 50 ppm oxygen, it's almost half of the original corrosion resistant. So in the application during the service, it can get corroded very easily, very fast. Let's see, this is the 50 ppm, 02, and 50 ppm is number 3. Even this is not accepted. It can cause a significant corrosion problem in the weldment area. And this is knife line attack. It is similar with the sensitization, but the affected materials are stabilized stainless steel with niobium and titanium. So they are, I repeat again, they are using titanium and niobium to take the carbons, so that they don't react with the chromium. And it's the same when you have knife attack. It's knife line attack. It seems like sensitization. So all the corrosive product can corrode the material. The mitigation is to heat treat again at the harsh heat extracting zone at 900 Celsius. So this is very similar with sensitization. And the problem with this is when the welding have quite high heat input, the niobium and titanium carbides, they dissolve again. So the carbides become free again. The carbon atom becomes free again. And then it's cooled immediately because it's located in the husk. And because of the fast cooling, the niobium and titanium doesn't combine with the carbons. So there is no more niobium and titanium carbides in the area, in the husk. So when the husk is exposed to the sensitization temperature below 1900, the 450 to 480 to 870, it reacts with the chromium and it causes sensitization. So the problem is that the chromium carbides happen at the lower temperature than 900. So when it exposed to that temperature below 900, the niobium and titanium still cannot take the carbon because it's not the temperature where they can take the carbon. The problem. Then chromium take the carbons and it get sensitization. So it's the same thing as sensitization, but it's just happened on the stabilized stainless steel. This is now we are entering stress corrosion cracking. Just to remind again, this is very important because it happens rapidly, very often unpredictable, and almost all weldments probably susceptible because they already have the stress inside the weldment, the residual stress. So most of the mitigation will be related to the reduction of the residual stress or post-weld heat treatment. This polyethylenic acid stress corrosion cracking is caused by sensitized stainless steel and nickel alloys. So it's still related to the previous damage mechanism, but the corrodant, if it's sensitization, you get corrosion rate, you get faster corrosion, but not cracking. But with the if you have the corrodant in the form of sulfides, moisture, and oxygen, then it may cause cracking. So the mitigation is to avoid contact with the atmosphere, so you don't get moisture and oxygen, or you use heat treated stabilized stainless steel, the one that I said before, the niobium and titanium addition stainless steel. So this is happen in a refinery mostly, where a lot of sulfur is getting treated. For example, in the boiler where you're using high sulfur fuels, when it's in operation, its temperature is very high. So it's the equipment is operated at the sensitization temperature. They are operated in the 500 to 850, 800 something Celsius. So they get sensitized. They get chromium carbides. But because of the operation is at the temperature, there is no wet corrosion. So it's no problem actually for the equipment to operate. You won't have corrosion because it's dry. The temperature is dry. The problem is when its equipment is getting shut down. When it's shut down, it goes to ambient. When it's ambient, there will be moisture from the environment. There will be exposure to the atmosphere. Then you have this. Then in the end, you have these three combination: sulfide scales, moisture, and oxygen, and cause cracking. This is example of the polyethylenic stress corrosion cracking. So it's always happen around welds because of the stress. It's a branching cracks, and only happen on the where the equipment operated at sensitization temperature with sulfur compound. If you don't have the sulfur compound, then you will not have this polyethylenic acid stress corrosion cracking. Another form of cracking is amine stress corrosion cracking, but this is only happen to carbon steel. The corrodant is contaminated amine. Most of the time is contaminated by carbon dioxide or H2S. And normally this is also in oil and gas. This is used for gas treating. They treat the gas to take the CO2 and H2S so they can sell the gas like LPG or LNG. The mitigation is simple. It's just post-welding treatment. And normally we refer to NACE SP0472. In this standard, there is already explanation about how high the temperatures to be used for the post-welding treatment. And just to make sure that if it's fresh amine, it's not susceptible. It's resistant from the amine stress corrosion cracking, only in contaminated amine. And actually, it depends on the type of amine, depends on temperature, depends on the stress level. But from the safe side, normally when you have carbon steel in the amine environment, you just post-weld heat treat it anyway for the safe side. Because normally this amine system is an important system in the refinery. So if it's getting shut down because of corrosion, then you have a lot of problem in the whole refinery. So it's better to post-weld treatment the welds when you have the amine service. Or you can, the most commonly referenced standard is to refer to API RP945. But in this API, then one of the clause to PwC is referring back to the next SP0472. This is the example of amine stress corrosion cracking. The first one, when it's not post-weld heat treatment, so this is the area where you have very high stress in the husk, it's cracked. And the second one is from the arc strike. This is also very high stress in this area, so this crack initiating from this area. And this is leaks occurred after 30 years of service. So as I said before, the stress corrosion cracking you cannot predict. You can have it tomorrow, or maybe you are safe from cracking for many years. That's the problem. You cannot know. So it's always recommended to be on the safe side when you have this stress corrosion cracking potential. Another one is carbonate stress corrosion cracking is in the carbon steel. The corrosion is when you have carbonate, CO3. The same mitigation you can refer to the NACE standard. Oh yeah, this NACE standard consists of many mitigation to environmental cracking. So not only amine, not only H2S, but many cracking to carbon steel. You can read the standard and you can get some information about it. This carbonate also normally happen at a relatively high pH. When there is ammonia or H2S, it will increase the susceptibility to carbonate cracking. But again, for the safe side, is always PWHT, the Weldment area. So this also happened quite a lot in the non-PWHT Weldments. Also mostly happen in refinery. This is one of the examples. You can see the cracks is longitudinal with the weldments. This is the same. Caustic stress corrosion cracking. Affecting materials, carbon steel and stainless steel, they are both susceptible to these cracks. The corrosion are caustic, natrium NaOH or KOH, natrium hydroxide or kalium hydroxide. This also happen mostly in caustic plant or refinery because they were both using caustic quite a lot. There are two types of mitigation: post-weld heat treatment. But sometimes post-weld heat treatment is not enough, depend on the caustic concentration and temperature. The alternative is upgrade to nickel alloys, where it's more resistant. Yes, there is a maximum temperature limit before the need to upgrade material to nickel alloys, despite PWHT. PWHT just to extend the operational range, but not to all range of concentration and temperature. But even if you upgrade to nickel alloys, you need to make sure that there is no molten caustic is present, because they also can experience stress corrosion cracking when molten caustic is there. And it's also, you can see the NACE SP0403 to read about this caustic stress corrosion cracking. There's a list of other mitigation process over there. But what I said is just only for the weldments. And okay, this is the curve, the chart where materials can operate. For example, if you see on the left side, it's for area A is for carbon steel without post-weld heat treatment. So in the caustic, you can, for example, in 30% caustic natrium hydroxide, if you are using carbon steel without post-welding treatment, you can operate to 60 Celsius. If you want to operate in 70 Celsius, then you have to post-welding treat the carbon steel. But if you want to operate even more, for example, in 100 Celsius, then you need to change the material to nickel alloys, or it will still crack even if you already post-welded it. Stainless steel is the same. Sometimes it's even worse than carbon steel. So if you upgrade to stainless steel, it doesn't affect the cracking resistance very much. You can see in the 30% caustic, the maximum temperature is 100 Celsius. It's not very different from the post-weld heat treated carbon steel. It has just a little bit higher resistance, but not a lot. The one that has significantly higher is nickel alloys. So this is what we can see. The left side, when you didn't etch the material, is the same area, same material, same cracks. So this is in a non-PWHT surface. This is the cracks that you can see. Chloride stress corrosion cracking is next. It's affected only stainless steel. Carbon steel is not affected. Nickel alloys is not affected. The corrosion is chlorides. When you have chlorides, you can have a stress corrosion cracking to stainless steel. The mitigation method are material upgrade and limit the temperature. Increasing nickel content or ferrite content is increasing the resistance to chloride. That's why nickel alloys normally is considered very resistant to chloride stress corrosion cracking. And duplex material, where you have high ferrite content, or ferritic stainless steel, is also considered very resistant to chloride stress corrosion cracking. When I say resistant, is high resistant, but not immune. In a very high temperature or very high chloride content, some of this material can still crack, but you need a very, very high parameter variables for that. But normally you don't find it in the actual application. So this is the general guidelines of the application. So if you have 304, 316 series material stainless steel, the maximum limit is 60 Celsius. And when you're using super duplex or duplex can have allowance to 100 Celsius. Super duplex can have 110 Celsius. But this is just general guidelines. For if you have a specific application, you need to consult with the corrosion engineer if this material still can be used or not. This is just general rule of thumb. You can see here this example of the stress corrosion cracking in 316L is almost always happen not in the weldment area, but in the husk area. Because normally in the weldments, the stainless steel have some residual ferrite, delta ferrite. So sometimes the weldment area is more resistant to crack than the husk area. This time is on the stress concentration area, it's on the toe. This is very high stress over here, so it can start cracking. I think this is the last one. The sulfide stress corrosion cracking. This happens a lot in the oil and gas industry, where you have H2S. All materials are susceptible, can crack. Carbon steel, stainless steel, nickel alloys, they are all can crack. The corrosion is H2S. The mitigation is to limit the strength. Limiting the hardness is almost the same with limiting the strength. So for all materials, when the hardness level is not exceeding certain numbers, it can be considered resistant to sulfide stress corrosion cracking. For carbon steel, there are many mitigation other than hardness limitation, but it's like post-W heat treatment, post-weld heat treatment, tempered bit welding, cooling rate control, and restriction to carbon equivalent. So this is the general mechanism. The higher the strength, the more susceptible it is. But why hardness is used? Because it's the easiest method to measure the material strength. Because it's linear, strength and hardness is linear. So when hardness is used, is somehow equal to strength. Normally the limits are 22 Rockwell scale or 248 Vickers scale. Normally that's the limited the rule of thumb. And cold forming to the materials, for example, bending is not recommended and it shall be avoided. Do not cold forming the materials when you have this surface, H2S surface, because some cold form materials can have a very high internal stress in the materials, but it doesn't reflect on the hardness. So the hardness value sometimes can still below the guidelines, but because of the very high stress inside, it still can crack. So it's hard to measure cold forming effect to the crack resistance. So it's almost always avoided for the cold forming in H2S. And yes, this is the most common reference standard. The 0175 is for upstream and 0103 is for refineries. This example of the sulfide stress cracking, you can see it start on the very hard welded surface. It's reaching this is by Brinell, so it's very hard on the surface, so it starts to crack even when the hardness is already low. But when the crack starts, it's just propagate. It doesn't matter how much hardness left in the material. This is the same. It is for the pressure vessel. It's also happened on the weldment area. Okay, that's all the common corrosion problem to the welding. But there is also treatment, how to improve corrosion resistance. This is especially important for corrosion resistant alloys like stainless steel or nickel alloys. So welding gas selection, for some alloys have nitrogen content in the metals. Nitrogen is very volatile. So when you weld, the nitrogen can escape to the atmosphere. So sometimes you need to add nitrogen gas on the shielding or in the backing gas to avoid the nitrogen loss to the atmosphere. When you have nitrogen loss, for example, in duplex is duplex stainless is highly alloyed with nitrogen. It reduces the corrosion resistance a lot. Also, if possible, it's recommended to always pickle the surface because it removes all the contaminants and renew the oxide layer on the corrosion resistant material. This example of the welding gas selection and surface treatment to duplex material. So as you can see, this is the CPT, same like before, the critical pitting temperature. Higher is better. This is as welded with the argon and formier, argon, nitrogen, and formier. So the one when you weld with nitrogen, it has better corrosion resistance. On the going to the right is the surface treatment. If you clean the surface, the cleaner the surface, the higher corrosion resistance of the material. So again, it's always important to, if possible, if you're like welding a big pipe, then you can you can pickle the material. But sometimes you have to satisfy with the as welded one. For example, like welding a small pipe, you cannot pickle the inside of the pipe, so you have to settle with this one. But what you can vary, but the variable can be adjusted. You can add, you can modify the gas to give better corrosion resistance. Now about post-weld heat treatment, this is commonly done to avoid stress corrosion cracking because it's reduced the residual stress level in the weldments. And this is mostly applied only for carbon steel. When you apply to stainless steel, it will cause another problem. Like I said, post-weld heat treatment is around 600 up to 650 Celsius. So it's on the sensitization temperature. So normally we avoid it to stainless steel because it's make it susceptible to another corrosion problems. And the temperature normally depends on the standard. You need to refer depend on the surface. So for example, if you're amine, probably definitely have different temperature, heat treatment temperature than carbonates. So this is, you can refer to these standards or other standards. And sometimes you cannot avoid, but it's very rare. But sometimes you cannot avoid to post weld the corrosion resistant alloys. Maybe stainless steel you need to post weld, probably because of the coat requirement or because of the thickness. Then what you can do is to qualify the welding parameters during the PQR. PQR in the PQR you need to do the qualification test. The samples need to be corrosion tested to ensure that the application of post-weld treatment does not affect the corrosion resistance of the materials. If you don't do this, then it's possible during the service the stainless steel will get corrosion because of the sensitization. And yes, why corrosion qualification test is very important during the PQR. The test is depends, the type of test depend on the material and depend on the environment, depend on the what is the corrosive substance. If you need to know the material type and the environment that it will be exposed to. And why this is important? Because not like mechanical defects, not like strength. Normally the PQR is related only to the mechanical aspect of weldments, but they don't really see the corrosion aspect of the weldments. And it's hard to detect if the material is susceptible to certain corrosion or not. Although sometimes hardness can be seen. If it's very hard, then possibly there's a high possibility that it can impact the stress corrosion cracking susceptibility. But for corrosion because of the media, the general corrosion type or localized corrosion type, like pitting corrosion, it's impossible to detect from the mechanical testing. So you need to add corrosion testing during the PQR. And why this is important also because you cannot see the corrosion happen after welding. You need to have certain period of time to realize that this weld have corrosion problem, and this is very problematic with important equipment because normally if you make something from corrosion from stainless steel, let's say, you reduce the inspection period because you are quite sure that this equipment will last a lot longer than when equipment is made by carbon steel. This is the main problem. So no, many times it failed before you inspect the equipment because of you have this because you didn't test the corrosion resistant during the PQR. Also, this test, I don't think this is very expensive, but the 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 consequences can be expensive. If you are using corrosion resistant alloys, stainless steel, nickel alloys, normally it's used for important equipment in the facility, in the plant, in the refineries. So when it fails, it's the damage, the cost of damage is even higher than the corrosion test itself. If you corrosion test, maybe you only spend several hundred of dollars, but when the equipment failed, you lose thousand or ten of thousand of dollars. And this corrosion tests are, there are a lot of possible corrosion tests. There are different standards of corrosion tests, and most of the standard is only to know weld quality. But if you want to know the real corrosion resistance of the weld, you need to test with actual weld fluid and the worst possible welding parameters. So you can know the real performance of your weldments, the real corrosion resistance of your weldments. And always set certain criteria during the corrosion test. So avoid dispute between the fabricators and the users. If you have the, normally in the standard, they don't provide a certain criteria. So they just provide the test method. But you need to set the criteria before the test. For example, there should not be pitting at 40 Celsius. You need to set it in the test requirement. If you don't set it, then the result can be disputed. The fabricator can say 30 Celsius you don't have it is good, but what you really want is 40 Celsius. But it will be disputed. It will be messy. So it's always better to state the acceptance criteria. This happens a lot because normally in the specification we just say test with ASTM G48. That's it. But now what is the acceptance criteria? And they test, and when the test result is not according to your expectation, then it's gonna have a problem because it's money. You need to test it again with, and you spend more money. And these are the most common corrosion tests to know the weld quality. The STM 8262, this is for the sensitization of stainless steel. G48, sensitization to nickel alloys. G48, resistance of stainless steel and nickel alloys. Sorry, I forgot to add it. Stainless steel and nickel alloys to chloride pitting and crevice corrosion. The NASTM 0177 to chloride stress corrosion cracking and sulfide stress corrosion cracking. Of metals, carbon steel, stainless and nickel alloys. The TM0198 is for corrosion resistant alloys, stainless steel and nickel alloys to chloride and sulfide stress corrosion cracking. But again, these tests are just to measure the weld quality is good, but it doesn't represent actual fluid condition. So if you pass this one of these tests, it doesn't mean that it will perform in the actual condition. Passing this test means that the result of the weldments are good enough. And this is, we are almost at the end of the presentation. We have still a lot of time. This common weld practice. So this is what I normally check in the in the welding specification. So it's better to select the correct parent and filler material selection. So for it is more important for the first one, the preferential wet corrosion. So it needed to minimize the galvanic effect. So the weldment is not faster, it's not experience faster corrosion than the parent material. And fully clean all the joints, especially for corrosion resistant material. If you have moisture left or residual oil on the joint, then it will impact the corrosion resistance a lot. And if possible, the design should have a flat bits and low profile, so to avoid crevice and to avoid stress concentration, especially when it's related to stress corrosion cracking. And complete penetration is preferred for the corrosion resistant material, because if there is a space in between, it can that area can be the start of the corrosion. And this is for the surface treatment. So maximum corrosion resistance can be achieved from smooth surface, no heat tints, no foreign particles, no irregularities, and pickled surface. And for corrosion resistant material, try to avoid contamination, try to avoid contact with carbon steel. Sometimes you put the stainless steel pipe to carbon steel table, then it's bad because it's contaminated the stainless steel. Or you use the same hammer for slack removal. You hammer the same hammer, it can contaminate the stainless steel. And if possible, to weld with filler, because if it's autogenous, they may cause problems because of unwanted phases precipitation or increase susceptibility to crack and corrosion. Or if it's a must, if autogenous weld cannot be avoided, proper post-welding treatment is to be completed. And this parent metal chemical composition and heat treatment shall be specified in the before creating welding specification, because some heat sensitive alloys, because chemical composition is very related to the hash. If you have very bad chemical composition, you can result in very bad heat affected zones, because welding consumables cannot help heat affected zones. It's only help the weld metal, the fusion zone, but cannot help the heat affected zones. And this is just precaution when you are inspecting the welding. If you are using basic flux, it's harder to remove, and so can cause crevice, and it can be initiate area for corrosion attack. Dissimilar welding, if it's carbon corrosion resistant to corrosion resistant, if it's very different in grades, for example, stainless steel to alloy 625, you need to have concern, because some chemical element dilution can cause unwanted effects. For example, creating of nitrites and other stuff. It needs to be seen on case-to-case basis. But for carbon steel to corrosion resistant material, normally have no problem, because the design normally based on the carbon steel. But if it's overlay welding, please consider dilution effect. So because the corrosion resistant material can have reduction in the chemical elements, so it have less resistance than before. For repair, this is common specification for repair. If you have defects removal, try to remove it completely with the hash. Provide enough access after repair, so you need to inspect it again, and limit the repair if possible. If it's duplex, probably you cannot repair it. You need to cut and re-weld again, and have special repair welding specification and PQR, including the corrosion test, just to make sure that the repair process will have still good corrosion resistance to the material. This is the one that we don't want to have, failure analysis. When it really happens during the service, what normally I do during the failure analysis. First, normally I do check the PQR, if does it include corrosion test, does the parameter similar to actual welding in the field. If it doesn't have a corrosion test, then the PQR is questionable. You need to qualify it again to see if the weld have good corrosion resistance. Then check the specification. Sometimes the welding engineer want to make less WPS, so the variables are too tight or are too wide. So these wide variables can have a wide effect to the corrosion resistance. Also need to check the parents and consumables. The combination is good or not. Recheck the fluid properties. This may not related to the welding, but this is related to the surface itself. Probably there was upset condition. For example, the chloride content suddenly getting high, or the H2S content suddenly getting high, then it may cause the increased corrosion on the weld area. Then the last one is to check inspection record. So you need to find if there is any discontinuity that can be detrimental to corrosion. Some discontinuity can be accepted by the inspector, but it may not impact the mechanical, but it may impact the corrosion. And it was the combination of the parent filler and the gas selection correct? Were the weld ones are cleaning? Were they pickle? Was oxygen continuously measured? Were the welders properly qualified? So these are stuff that when it happened, normally these are the stuff that I normally check. When there is no answer from those stuff, then you need to take the samples to laboratory to do the proper failure analysis. This is one case of this. The last one, the last part of the slide, case study of super duplex stainless steel welding. The base material are super duplex. This solution annealed to 1,100 Celsius, so the microstructure are uniform. The ferrite to arsenic balance are very good. It's on 55%. Ferrite number is 64. This is the chemical composition. It's very high in nitrogen, very good. High moly, high nickel. So this is a perfect material. So, but now we are going to use 4-phase autogenous weld, thick weld with HIS low heat input and high heat input. The shielding gas will be just argon. So if you see the microstructure, this is a very balanced, very good. This is the original microstructure from the parent material. But when you see the Weldment microstructure, this for the low heat input and high input, you can see the effect. In the high heat input, you have a lot of secondary phase precipitation. Why? Later we can see it. So this is L. L is low heat input. 1 is 1 pass. 4 is 4 pass. You can see the effect of the heat input to microstructure. Low heat input, no, and only 1 pass. You have no secondary phase precipitation, no unwanted phase. But even if low heat input, but you have a lot of passes, welding pass, you can see some black spots. These black spots, black spots. When you have high heat input, but only 1 pass, you have very minimum black spots. But high input and a lot of pass, a lot of welding pass, you have many more secondary precipitation. So heat input is very important in sensitive material like duplex. And this is what happened on the Weldment area. This what I've said before: low heat input 1 pass, low heat input 2 pass, high input 1 pass, high heat input 2 pass. The austenite have very low. There's a very low austenite phase balance in the weld area. The higher the heat input, the less austenite balance. Why? Because the nitrogen is losing. You're losing nitrogen if you are using only argon gas. The nitrogen gets out to the atmosphere. That's why the austenite phase are very low. The ferrite content is not affected by nitrogen, so it still maintains very high. In combination with nitrogen loss, you also have very fast cooling. This is autogenous weld. So very fast cooling create a very high ferrite content in the weld zone. This is unwanted. It's a very low corrosion resistance. It is very prone to crack. It is very low impact strength. So the higher heat input has a very high ferrite content. The low heat input also very high. It's also not acceptable, but still lower than the high heat input. The base metal is here. This is the first pass. This is the fourth pass. So the more heat input you give, the more ferrite content you get, and it's not wanted because it's not balanced anymore. So this is why weldment corrosion is important, because there are too many variables during the welding. Heat input can be variables, number of pass can be variables, welding gas can be variables. The parent metal composition also can be variables, and that's why corrosion test is need to be done before welding during the PQR, so to ensure that this kind of damage does not happen. What can happen? Secondary phase, corrosion resistance reduction, imbalance phase, and we don't want that. So I take too much time. So thank you very much. I hope I was not too fast, and I hope everything can be understood easily. I'm sorry if I have something wrong, and please correct me. I'm open to discussion. Thank you.
Yeah, Andrew, thanks for the beautiful presentation. See, in the question and answer session, there are a few questions which I think you can take up.
Okay, I'm reading the question and answer now. I'm starting with the open one.
Yeah.
So, okay, before I'm answering, I need to clarify to all the participants that I may not be able to answer a question related to welding process, because I'm not the expert here. I know the basic, but I cannot answer if you ask a very advanced question. But if it's basic question, probably I can still answer that.
No, you please go ahead. Wherever required, I will teach you.
Okay, the first I see from Manoj, he's asking for certificate, so I will pass. I'm not going to answer. It's for you. And second is from Ashif. What is it? How to prevent from corrosion saw welding wire due to long storage and the flare nearer to the seashore. So is this the corrosion of the wire? If it's the corrosion of the wire, then
yeah, it is the nothing corrosion of the wire.
Yeah, your preservation procedure should have it. And normally, yeah, as Edmund Zaraspe have answered, it should be properly storage, and if possible to avoid contamination to the moisture. So that's my answer, similar to Edmond. Thank you, Edmond. Next one is from Francis Lobo. The color tint during the cost of heat tint during welding of super duplex stainless steel and impact of this corrosion, color tint to surface corrosion. The impact is a lot. As I said before, the heat tint is actually the oxide layer that is very thick and porous, and because of the reaction with the oxygen at high temperature. So you want to remove this, and also remove some part of the metals below, because the metals below the heat tint is metals with very low chromium. So you need to remove this as well to get the layer of metals with nominal chromium as the parent material. And how to achieve acceptable color? First is to use oxygen measuring device during the welding. So when the operator, the welder are welding the material, another helper is putting this oxygen measuring device to ensure that there is very less oxygen contamination. And then if there is contamination, the welder can adjust the gas flow, and or probably the gas flow mostly. And sometimes they need to add another equipment for trailing gas, another gas producing equipment to ensure that in addition to the original gas from the torch. But it also always depends on the condition. If it's very windy, normally don't do weld at all. How about dissimilar welding? Dissimilar welding, it should be, I think already explained. If it's stainless steel to stainless steel, normally you have no problem. Stainless steel with high nickel alloys probably have problem because of the different chemical composition and different reaction from the higher alloy materials. The higher nickel alloys a lot of times have some very exotic addition like tungsten, niobium, and other stuff. So you need to ensure that the addition of the higher nickel alloys doesn't impact the weldment corrosion. If it's stainless steel to carbon steel, normally you have no problem as well, because it's the equipment is designed for carbon steel. It's useless to weld with the stainless steel. Sensitization on all stainless steel or only in austenitic stainless steel? It can happen to all stainless steel, but normally you don't find it in duplex or ferritic stainless steel, because normally they don't operate in that sensitization temperature. Also, the difference is if for example 304, you have 304 and 304L, you need to differ between the high carbon and low carbon. But if it's duplex, if you specify the duplex, it's already low carbon in the specification, so you cannot get a high carbon duplex. When you buy a duplex, it should be only in the low carbon because it's already in the specification. So it is not susceptible to sensitization. Next one, why sensitization occurs in austenitic stainless steel but not happen in 400 series? Yes, because the 400 series doesn't use, it's not being used in the sensitization range. Can we get the PowerPoint? It's for you to answer. What will be the solution for heat tints? I already answered before. What methods are used to find heat tints? It's visual. You can see it directly. You can refer to AWS or the Norstock standard. Where is it? I lost it. Okay, now. This team, the IIW. Oh, nothing. Is there any corrosion to test PWC on carbon steel weld? Yes, you can use the normal corrosion test, the wheel test, but for the weldment area, you can most of the time you can see the difference of the corrosion rate. So this method is normally used to testing corrosion inhibitor, but you can use the same method. I don't remember the specification to refer to, but if you Google it, it's easily to find because it's very common. I thought from material selection by selecting high number of trend, then the more resistant stainless steel to precipitating corrosion. So this can be a method of prevention, correct? Yes, correct. The higher the PRE, the more resistant to the localized corrosion. The problem is on the weldments, you can have higher PRE in the weldments, but you can have another phases that can cause corrosion. So it doesn't, even if you have the higher PRE, the for example intermetric phase, if in duplex, super duplex has very high PRE, but if you weld it wrongly, then you have intermetallic phase, sigma phase, then the corrosion starts there. The other area probably free of corrosion, but the pitting corrosion will start on that phases. From Bharat West Namuduru, can you advise about standard for picking and pacification on Inconel 625 overlay? The higher the alloy, the more resistant is to prickling and pacification. So I have to be honest with you. I don't know if there is standard for high nickel alloys material, but normally we ask the method to the alloy manufacturer. I'm sure they have this procedure. Then if you, for example, if you are buying Inconel 625 from a manufacturer, you ask the manufacturer, they will give it to you. I bet 100% they have the procedure for pickling and pacification. But I never know if there's standard for this high nickel alloys material. Maybe there is, but I don't know. I need to find out. Can you please light on hydrogen disbonding test from Sachin? This is the first time I heard about hydrogen disbonding test. So
yeah,
I'm sorry.
Andre, yes? You want me to take up that?
Take what? Sorry.
Yeah, you want me to take that question on hydrogen disbonding?
No, because I don't know. I cannot answer.
So I will answer. Yeah.
Okay, please.
For the participant. So this test is a method for evaluation of hydrogen-induced disbonding. For example, suppose we make a reactor with with an overlay on the ID. Okay, and when during the operation, it is subject to very high pressure and temperature. So what is going to happen to the overlay? Is there going to be a disbonding between the base metal and the weld overlay? So there is a test called hydrogen disbonding test, which is done as per ASTM G148, if I remember correctly. So there you put the sample on an autoclave and you simulate the pressure and temperature and the pressure of the hydrogen partial pressure. So the sample, I think, is kept for almost 2 days, and you take out the sample and carry out a UT ultrasonic examination to find out whether any disbonding has happened. So this entire procedure has been very well explained in ASTM standard G148. Yeah, you can move further.
All right. Thank you. I hope it answered your question, Sachin. Now is from Mohan Suburaj. The electrode E309L, all wet metal will pass intergranular corrosion practice E after sensitization. If it's correctly welded, I think it will pass the intergranular corrosion. That is why this is normally used for weld quality test. If the weld is good, the procedure is good, then it will pass the, I think this is STMA 262. This is the test to make sure that the weldment, the weld procedure, the weld process are good. But the electrodes are low carbon, so it should pass the test just to make sure that the procedure and the welding process are proper. This is still about the packing. I'm not capable to answer about the packing. Is there any other method from Sudhir? Any method other than picking precipitation to avoid corrosion in stainless steel 316 material? Actually, the pickling and pacification is to increase the corrosion resistance, but as weld condition can also be used. just in case. But you need to like I said, avoid the heat tint, avoid the intermetallic phases, avoid sensitization. It can have a good corrosion resistance. If you I'm sorry, I forgot, this is 316 without L. Then 316 without L, then there's a high chance for you to get sensitization, and picking and passivation will not help because the sensitization happen all the harsh thickness. So even if you remove the top layer, the bottom layer, you will still experience sensitization. So I don't think picking and passivation help to access 316 without low carbon. If you have low carbon, pickling and passivation will increase its corrosion resistance. But if you use it as welded, it's also very common to use it as welded. For example, in a pipe, you cannot pickle and passivation inside the pipe. You need to have it in as welded condition, but with the backing gas, with the proper backing gas. What is the impact temperature for nickel alloy and why heat treatment is not required? It depends on the nickel alloys. I would say there are a lot of types of nickel alloys, but normally it's very high, very low. You can have it in the very low temperature, no problem, because nickel is FCC on the atomic structure, and FCC are normally well known for the high impact resistance. And why heat treatment is not required? If you mean heat treatment is post-weld heat treatment, then it is not required because possible of sensitization. The same with stainless steel. Nickel alloy is also possible to have this sensitization because it still contain chromium, it still contain carbons. For cast alloy, why corrosion rate is high at high temperatures? Depends also from Arun Chandra. It also depends on the environment. If you have a environment where cast alloy is not suitable, then it also can corrode quite fast. And why corrosion rate high? I think it's general because high temperature means high reaction rate. It's not only for cast alloy. In all metals, in carbon steel and stainless steel, high temperature will cause higher corrosion problem. The same, like for example, before I said the CPT, critical pitting temperature. So the higher critical pitting temperature means the higher resistance. So better material is used. So lower material cannot resist higher temperature test because it will corrode. You need to upgrade to the material if you want to use it at higher temperatures. In Sierra Weld overlay from Sanjoy Sarkar, what is the impact of Fa content in the filler metal? What I know is the Fa content will dilute the concentration of the filler metal. For example, if you fill with nickel alloys using the weld overlay, for example, you have 20% dilution. You have this 20% ferrous go inside the fusion zone, then it will significantly impact the corrosion resistance of the weld overlay. So that is why most often weld overlay is done at minimum 2 layers. So the first layer is to absorb this Fa dilution, and the second layer you have very minimum Fa dilution, so you can still have a very good corrosion resistance of CRA weld overlay.
Yeah, Andre, further to that, suppose we take a non-ferrous weld overlay, okay, they also specify some amount of minimum Fe onto the wire. Basically, it is to see that you get enough strength and erosion resistance through solid solution precipitation hardening. So it also depends on the type of overlay which we carry.
I see. Yeah, it's from mechanical properties point of view.
Correct, correct. So we have to have a balance between the corrosion as well as the strength.
Good. Thanks for the input.
Yeah, please.
Okay, I'll go. We almost to the end. The AWS specification for heat tint acceptance criteria is AWS 18.2. If the presentation will be shared later on, there is the references I put there. You can see it. How to prevent sigma phase occurrence while welding duplex stainless steel? Any tips from Arun Chandra? I would say a lot of tips. The first is to limit the heat input, and then the second one is to use higher alloy duplex. For example, there are two types of duplex, the 31803 and 32205. Then you need to use the 32205 one, not the 31803, because the 32205 are higher alloy than the 31803. So it has more nitrogen. The more nitrogen, the less sigma phase susceptibility. Also try, if you are welding, for example, super duplex, you have super duplex, some manufacturer add tungsten, some manufacturer add yes, mostly they add tungsten for the corrosion resistance. The tungsten addition increase the susceptibility. So if you think your process will have sigma phase, then try to buy super duplex without tungsten. So yes, the most but the most significant effect is the heat input. Try to minimize it as much as possible, especially when you are doing multi-pass welding. There is a nomogram of heat input for duplex. It can be used to predict the duplex thickness, the heat input, and the cooling rate for the welding, and then you can put the cooling rate into the sensitization, not the sensitization, the sigma phase diagram. If you can see if the cooling rate will reach the nose or it will not reach the nose. You need to find this in the handbook. You need to find the nomogram in the handbook. If you find the nomogram, then it's easy for you to calculate the cooling rate that can be used for duplex. In the welding super duplex, which test I can use to ensure the welding joint is corrosion resistant? Most of the specifications are using G48 method A at 40 Celsius. This is for the best. This is the best for the best possible weld quality of super duplex. G48 method A, but the acceptance criteria is 40 Celsius. If the test can reach this 40 Celsius without pitting, then the weld is considered good. This is the highest specification I've seen so far. Pickling and precipitation will help to remove this heat tint effect. Depends on the thickness. Sometimes you need to grind it first just to make sure everything is removed. You don't want to risk your stainless steel or nickel alloys to have corrosion later on. It's easy. You brush it first with stainless steel brush or grind it, and then you pickle and passivation. That's the best method that I can suggest. If you just pickling and passivation, maybe can, but it probably would take sometimes to remove all the scales, because it's a quite thick scales and quite hard scales. Is there metallurgical reasons why 400 series not sensitized? I already answered before. It is normally not used in the welded condition. It's a ferritic stainless steel, and it is not used in the temperature where sensitization happen. There are also, I have to add that there are also weldable ferritic stainless steel, but the carbon content is low, and it was added titanium to take the carbon. So there is 500 series that can be welded, but it's not a lot. It's not common. Normally, you don't use it for welding. Okay, I think that's all.
Yeah, I think we are done with all the question answers. Thank you so much for taking the entire questions.
No, I
think,
thank you.
Yeah, Nimesh, over to you.
All right. I think Mr. Malge is there.
Yeah, I'm there.
Okay. I think thanks a lot, Andy, for a very beautiful presentation. And I guess lots of people have commented and they've really enjoyed the simplicity in which you have explained the whole corrosion impact. And it's a very detailed presentation and it requires the time that you've given it. And thanks a lot for simplifying it and going through things the way you have. I'll now pass it on to Mr. Malge to convey the vote of thanks.
Thank you, Nimesh. Dear all participants, Mr. Andre, the speaker, and technical team, it gives an immense pleasure for me to propose vote of thanks. Okay. The presentation was fantastic, meticulous, and it is very important and interesting and informative talk. The very fact that people, around 100 people stayed till end, till the last question is answered, that itself indicates the interest generated during the presentation. Presentation was so meticulously designed and delivered, starting from the basics, why weldment are susceptible for corrosion, till the importance of corrosion qualification test, ending with failure analysis and case studies in super duplex stainless steel. Mr. Andre covered a lot of topics in the presentation, weld metal corrosion factors, then specific corrosion test, amine corrosion, stress corrosion cracking, carbonate, caustic soda, chloride, sulfide, etc., etc., etc. You name anything in the corrosion area, he has dealt with. So thank you, Andre, for your very, very important and very nice presentation covering most of the corrosion areas in the weldments. I also thank all the participants without whose presence this talk was not talk is important. So I thank all the participants for having taken interest and be present till end of the question. I also thank our technical team, basically Dr. Krishnan, Nimesh Shonai, and Abhishek Vyas, for having taken the trouble organizing and conducting this talk across the globe, I should say. I don't know, people from all over the globe must have been participated. Thanks once and again, and we hope to see you again in the next Weld Tech Talk, what is planned, and it will be informed to you all. Thanks to everyone once again. Thank you.
Thank you very much.
Thank
Thank you very much.
Thank you, Andre. Time to sign off.
Thank you, Mr. Ashok. Thank you, Mr. Nimesh. Thank you, Mr. Krishnan. It's been a great pleasure.
Thank you, Mr. Andre, for having taken your time and presenting such a wonderful topic and made it so easy that everyone could understand. Thank you.
Andre. Thank you as well for arranging this. And for the presentation, I give my consent for you to give it to the participants.
Thank you very much. And also your email ID, people want to get in touch with you now.
Oh.
They want to know which email ID they should connect with you on.
So you are in demand now.
If I can help, I will help. No problem.
Yeah. Okay. Thank you.
Okay. Thanks a lot.
Thank you.
Thank you very much.
Good evening and have a nice day.
Thank you.
Stay safe. Goodbye.
Bye.
Everybody.